So we're going to work in chapter 2, which is all about sets. And then we'll pretty much go chronological from this point. So the first section we're going to cover is our set concept. So kind of the basics, set up the introduction, go through all of our terminology for this. So really you've worked with sets a lot in your life without really realizing it. All a set is a collection of objects. You get a group of things together, that's classified as a set. The objects themselves involved in the set are called elements or members of the set. Okay. So as some small examples of different types of sets, you can have the birthdays of family members. That is a collection of objects or things. You can have football teams, any type of sports teams. You can have students in the class. Possibilities are endless, but these are a collection of some type of objects. Okay? The thing we want to make sure of is we don't want the set to vary from person to person. So we really want to work with some type of set that's called well-defined. So we say a set is well-defined if the elements are clearly determined. Okay. Regardless of the person creating the set. Okay. So let's try another example and give you some well-defined sets versus some not well-defined sets. Okay. So well-defined would be a list of holidays. You can Google that list. You might not know everything right off the top of your head, but that's okay. You know every holiday that is classified and would fall into this set. Okay. Another one could be Olympic cities. Okay. There's no subjectivity to that. This city hosted the Olympics or they didn't. So they're going to go in that set. Something that's not well defined could be like the best 3 movies or like the best foods. If I'm creating this set, I'm going to put particular things that I like and consider the best. Same thing with foods. There are certain foods I enjoy that other people might not say is their top choice. So that type of set varies from person to person. So ultimately, when something is subjective, or varies between different people, it won't be well defined. And we definitely don't want that. Okay? So pretty much everything we're going to work with will be well defined. You're going to see a lot of times we're going to work with numbers, or we're going to work with like different just list of things that we have. Okay? So ultimately, we have a lot of ways to write a set. These are great. I know exactly what's going to be inside of them, but sometimes we have a different approach that we need to take. So let's talk about different types of set notation. And so ultimately, there are 3 main methods to indicate what elements are in a set. we have description, roster method, and set builder notation. So let's go over the first two, and then we'll work with set builder notation in a little bit because that one can be a little irritating. But description is definitely our simplest one because this is how you verbally talk about something anyway. So here you verbally communicate the elements of the set. And for this, you can see the prior examples. Okay. All of these verbally communicate what those elements are going to be. Same thing up here, birthdays of family members, football teams. You know the type of things that are inside. You just don't have a full list of them, and that's okay. The roster method or roster form, probably should change this one to form too. It's a little bit better of a word. It's just like a roster in a classroom. It is a list of the students. So that's what you do for the roster form. You list the elements straight out. So we list the elements inside a set of braces. So basically, you're going to start your set by using some brace. You end your set by using another brace. Okay. So let's look at some examples of something in roster form and description. If you have the set of natural numbers, you can look this up in a book, but basically those are your counting numbers. So really this is given by an n. You don't need to know that, but in case you look it up. Basically those numbers are 1, 2, 3, 4, 5, and then that list keeps going on and on. You definitely cannot write every single natural number because a million is a natural number. You would not be able to write the numbers 1 through a million in your lifetime. So these little dot, dot, dots basically tell us to continue the pattern. And this is called an ellipsis. And so it indicates the remaining elements Macy, continue in the same pattern. So this way I know I'm basically going to go up by 1 each and every time. So a couple more of these. Let's look at the set of integers between -3 and 4. This is the following. So these are the numbers between, but not equal to -3 and 4. So this would be the numbers -2, -1, 0, 1, 2, and 3. And that is it. A lot of times we honestly like to label this set, so I'm going to call it A. Set A is equal to these things, just like this kind of funky n is equal to this set of natural numbers. Okay. And I'll do one more piggybacking off this last example. Let's look at the set of integers between -3 and 4 inclusive is the following. Since it's inclusive, that means I can equal -3 and 4. So I still get all of the same numbers as before, but now I can add -3 and 4. And I'll call this set B. Okay. All right. The last form we have is our set builder notation. And this really is a combination of the two. You're going to have these brackets that kind of tell you the set is falls in between here, but you have to give some type of conditions for everything that is going to go inside. So ultimately, this is commonly used in algebra. Okay. And so the best thing I can do is really give you something in set builder notation and kind of break down what each component means. So we're going to call this set D. And you still start that set with a brace. So this tells us set D is, the brace means the set of, and now I'm going to put a variable here. I'm going to call it X. So this is standing for our elements. Okay. So I'm going to take all of the elements such that some condition holds. So we're going to take all X, we're going to put a bar here, and that bar means such that whatever conditions you want hold. Okay. And then we end our set afterwards. So this is what you're going to be seeing every single time. This starting bit will always be the same, just the conditions are going to change from set to set. And so what goes here are the conditions, possibly multiple, that X must meet to be a member of set D. Okay. So there's another symbol that's going to pop up relatively frequently when you see it as conditions. It's going to kind of look like an E. So it's just a strange looking E, but it's actually a Greek letter. So you're going to see this symbol will commonly be used in the conditions. And it means is an element of. Okay. So what do I mean by that? Give you a small example. If you have a set D, which has the elements winter, spring, fall, and summer, then we can say that winter is an element of set D. So it belongs to this set. Since winter is a member of set D. Okay. And if I want to write this in set builder notation, we can also write D in set builder notation as follows. Okay. Our condition that we have to have hold is that the elements are seasons of the year. So we're going to take all elements X such that X is a season. Okay. Winter, fall, spring, and summer, they are seasons. So that is the condition we have to have. So this is our roster form. This is our set builder notation. If I'm just saying a description of my set, it's a set of seasons. Okay. All right, so let's try a few more examples working with these. We're going to list the elements in description and we're going to list them in roster form, given a set builder notation. So let's list the elements of set D, which is the set of X such that X belongs to the natural numbers and X is greater than 100. by first roster form. Okay. So I would actually list the elements of set D. And so again, this means it's a natural number and it's all the numbers greater than 100. So the first natural number bigger than 100 is 101. Then it's 102, 103, and that pattern just continues on forever. If we want to put this in description, the set D is the set of all elements X such that X is a natural number and X is greater than 100. Okay. So that is our set in description form. So I got one more example of this, and then we are going to talk about some last pieces, or last terminology, I should say. So last example, let's write the sets in set builder notation. So we're going to be given them in a different form. We want to put it in set builder. And the first set we're working with is A, which is Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. So these are all of the elements inside of our set. So in set builder notation, this is all elements X such that X is a planet in Earth's solar system. So that is the only condition that is set to be a member of this set. Do one more. We got set B, which is the numbers 1, 2, 3, 4. Keep going and following that pattern, but we're going to cut it off at 45. Okay. So we actually have a couple different ways we can write this. But either way, we're going to start with the same thing, X such that. You want to make sure you're stating X is a natural number, though. And if you state it like this, that's perfectly okay. And then I have a couple different things to put this range. I can say I start at 1 and I can equal that, and my X is trapped between 1 and 45. Again, I'm able to equal 1 and 45. But if I leave this out and I just put this range, that tells me I can pick numbers like 1.5 and decimals and things that I don't want. So I need to make sure I'm classifying, I'm only taking these natural numbers or integers. The other way you can write this is you still start out the same, but to condense X as a natural number, you can use X as an element of the natural numbers. And then if you don't want to include equal to signs, you're picking numbers between 0 and 46. So I can't equal those endpoints. Okay. All right. So that is really kind of the core of what our sets are. From this point, we're really going to kind of work with them. So we're going to manipulate them. We're going to talk about subsets. We're going to talk about Venn diagrams. We're going to do a whole bunch of stuff with these as the sections go along. So the last piece that falls inside this section are some fundamental set concepts. Okay. This is going to basically be more terminology and introduce some other types of notations. So first thing, if you even take a look at some of these, this has a set number of elements. Same thing here. It doesn't continue on forever. But if I scroll back a little bit, this continues on forever and ever and ever. So when you have a set number of elements, we say it's finite. Otherwise, it's going to be infinite. So ultimately, a set is said to be finite if it contains no elements or the number of elements is a natural number. I could have a million elements and it still be finite. It just can't continue forever. So a set that is not finite is said to be infinite. Okay. So kind of some strange things that actually happen if you think of any of your prior math classes. You solved equations and you got things like 3 is equal to 3 or x is equal to 3. For sets, something different can happen, or we use equals in a different set. So we say set A is equal to set B if and only if set A and set B contain exactly the same elements. So if that happens, we can use equals in our normal sense. So here we can write A is equal to B. Okay. But we have another form that's similar to this word, similar notation, but they don't have to have exactly the same thing. So let me give you a short example. If A has the elements A, B, and C, and B has the elements C, A, B. They're in a different order, but they're exactly the same thing that's inside. So these two sets are exactly the same. We can say set A and B are equal. Okay. Now, before I can talk about this other form of kind of equality, we've got to talk about another definition, which is the cardinal number. And what this does is it just tells you how many elements are inside the set. So the cardinal number of a set A, which is going to be symbolized in our book by N with A on the inside. This is the number of elements. In set A. Okay. So basically N is standing for number. Another notation you might see in other books that's also common is you'll see bars around set A, but our book doesn't use that, so we're not going to talk about it. So going back to this last example, if set A is the elements A, B, and C, there are 3 elements inside, so then the cardinal number of A is 3. Now, our interesting form of equality is the word that we use, equivalent. And basically that means I don't care about what's inside, I just care that they have the same number of elements. So we say set A is equivalent to set B if the cardinal numbers for each of them are the same. So basically they have the same number of elements. Okay. So let's look at some example we'll still use set A as the same. If A is the set A, B, C, and B is the set apple, banana, carrot, these two are equivalent, okay? So then the number of elements in A is the same as the number of elements in B. They both have 3 elements. So sets A and B are equivalent, but they're not equal. Because they don't have exactly the same thing inside. Okay. If you do have sets that are equal, we can create something called a one-to-one correspondence. So basically, I can match up each element to a different one in the set. It's one element to one in the other. Okay. So when sets have the same cardinality, or they have the same cardinal number, they can be placed in a one-to-one correspondence. And so let's look at 2 sets, give you an example of this. Set A will have 3 elements. We'll keep with the A, B, and C. Set B is our apple, banana, carrot. So one possibility is I just go ahead and pair the like letters up. So this is a one-to-one correspondence. Okay. A second possibility, can I go ahead and just duplicate this, get rid of my arrows, is I can pair things up in a completely different manner. Let's pair A and carrot, C and banana, B and apple. This is a second or a different one-to-one correspondence. Okay. Which is nice, but not the most useful for everything we're going to do. But in real life situations, this can be beneficial. So you compare numbers with different groupings of people. So I've got 2 more definitions left in this section, and then we're going to work with actually operations for these. And we're going to go through subsets first. But the last 2 definitions are really special type of sets. Okay? So sometimes you kind of have a contradiction, or you have a set that ends up containing nothing. We have a special symbol for that. So the set that contains no elements is called the empty set. Or null set. And is symbolized one of 2 ways. You either put braces with absolutely nothing inside, or you do a circle with a slash through it. Okay. So this is going to be important for us because sometimes we're going to look at overlaps of sets. There might be nothing overlapping the 2. So that's where we would use this empty set. A universal set, which is always going to be denoted with a U, is a set that contains all the elements. For a specific discussion. Okay. So basically the universal gathers everything imaginable that you need to talk about that discussion, but maybe you're only going to care about smaller portions of that. Like universal set could be all of the students at Polk State College. That is a lot of them. But then we're going to talk about smaller groupings within those. Okay? So this is our main terminology, and that is it for that section.